Okay, this is very easily solved, but you want to do the steps, you want to write out all the steps. And you want to write them out correctly, and be sure you multiply on the left. Because the way you solve this equation is you first find a piece of white chalk. What's blue chalk doing in my hand? Okay, the way you solve this equation, I put it there, okay. Is you multiply which gives you identity times x equals A inverse times B, which gives you x equals A inverse times B. Of course, we wrote that down last time. Make sure you understand the logic of that. You understand y over step works if you can find an inverse matrix. Sometimes you can't find an inverse matrix. And we see what happens with that, but you can in this case. Okay, so A inverse, the 2 by 2 matrix, you don't really have to do any work to do it. You just have to know what we derived last time. Up to the last step where it's getting too messy and I didn't trust myself, okay? I still don't know if that would have worked out. I'd like to find out, but a lot of things to do, just like you. Okay, so and we'll write it this way. A is this matrix, A inverse is the inverse of this matrix. And we do the inverse by flipping these two, the numbers in the main diagonal, and changing the sign of the secondary diagonal. So the matrix equation becomes this, because your original equation is this matrix times x equals this matrix times 7, 9. Multiplying on the left. If you try to multiply on the right, you can multiply 7 9s like this matrix, but you get something pretty weird. We're not going to worry about it right now. Actually, no, you can't even do it. If you have 7 9 on this side, your rows have only length 1 and your columns have length 2. It doesn't work. Okay. So anyhow, this gives us the identity matrix, 1, 0. If you multiply it out, you don't really have to do that. And I've already copied something down wrong. That's a 2 there, right? This is the identity times x, so that has to equal x. And now we just multiply. 5 times 7 is 35. 3 times 9 is 27. 27 and 35 is 62. And negative 4 times 7 is negative 28. This is 18, so that's negative 10. Okay. It doesn't look like that's going to work. Good. I think we did something wrong. Because 2 times 62 minus 3 times negative 10 is not 7. I'm not going to worry too much about it. This is the way it's done. Oh, wait a minute. Yeah, when I did the inverse matrix, I don't have the inverse matrix, right? I have to divide by 5 times 2 minus 3 times negative 4. Okay. So, no, not to do that. And 5 times 2 is 10, 3 times negative 4 is negative 12. That gives you 22. So this should have been over 22, over 22, over 22, over 22. Not going to be able to read it, but it's over 22. Okay. And of course, you understand where that came from, because when I did the reduction down to almost, the second to last step, the second row of our inverse matrix had the denominator A1, A11, A22 minus A21, A12. All these are over 22, so that's 62 over 22 is 31 over 11. This is negative 5 over 11. Okay. And that's going to work out. Check it, just like I did. I left something off, and I got an answer that made no sense, and I had to actually start thinking. Okay, and recognize that I made a mistake. Okay, and that kind of appears to work. 2 times 31 over 11 is about almost 6. Negative 5 over 11 times negative 3 is 15 over 11, which is a little more than 1. If we add something that's almost 6 to something that's a little more than 1, it's plausible that we get 7, right? And also 4 times 31 over 11, that's about 3. X is close to 3, y is about a half. So 3 times 4 is 12, minus 5 times a half is negative 2.5. 12 minus 2.5 is 9.5. So it's reasonably close. You can always check it, okay? You want to follow that process. Okay, well. And that procedure has been well established in your text and in your problems. If you haven't done those problems using an inverse matrix, write them out this way. And remember to divide by that thing. Okay? I pretended to forget so that I could emphasize the need for you to remember. Believe me? Okay. Yeah, I screwed it up. Okay. Now we want to reduce this matrix to upper triangular using elementary matrices. And that will lead me off on something that the LU decomposition, which your book kind of made a big deal of, and then ask you one trivial question at the end of the web assignment. Okay, I can get in and modify those assignments, but I'm trying to hold myself back so I don't overwhelm you. Okay, I could add a real problem there, but I've chosen not to. Okay, so matrix is, if I copy it down right, 2, 5, 1, 0, 3, 2, and no, it's 1, 3, 2, 1, 0, 1, 4. I gave you 0 here to make it a little easier. Okay. Well, first thing I'm going to do is take half of this row. Okay. Now, I could switch these 2 rows. Okay. But if you do an LU decomposition, you can't switch rows. Okay. So we're going to actually do an LU decomposition of this, but that starts by reducing the matrix to upper triangular form without switching any rows. Okay. So LU decomposition. Reduced to U form, which is upper triangular. Without switching rows. Okay, so we do that. Well, the first thing we want to do is half of this row, right? So we want to do half of row one. So we take the identity matrix. Gives us the elementary matrix, which we'll call E1, where we do half of row one. And most of you did that. I think everybody did that. I think I saw that elementary matrix in everybody's paper. Okay, so I'm happy with that. Let's take it a little further, okay? So there's our first elementary matrix. If I multiply yes, and I'm not going to write it all out. You can multiply matrices probably better than I can. But you're going to take half of everything in the first row. That's what this row is going to do. This row is going to multiply this column, this column, this column. That'll give you your first row. And then your second row is just multiplied by 0, 1, 0, which is gives you the second row, and the 0, 0, 1 here gives you the third row. Okay. And my gestures didn't make any sense, so ignore them. Okay. That gives you 1, 5 halves, 1 half, 1, 3, 2, 0, 1, 4. Then what do? We add -1 times the first row to the second. Put a circle where I shouldn't have. Okay, well, your elementary matrix gives you E2, which is 1, 0, 0, 1, 1, 0, 0, 0, 1. Just adding the first row. -1 times the first row to the second, be -1. I'm bound to screw something up by being careful. Okay, so then E2 times your matrix 1, 5 halves, 1 half, 1, 3, 2, 0, 1, 4 equal 1, 5 halves, 1 half. And incidentally, never use decimal equivalents. Okay, I don't think I've seen anybody do that. But if you have like 3/7, you can't, your decimal equivalent is just a repeating number. And you're going to make an error by rounding that off. Use the fractions, you avoid errors. Okay, okay, then we multiply by -1, 1, 0, we get 0, 1 half, and 3 halves, 0, 0, 0, 1, 4. Okay. Then what do we have to do? Well, we're going to multiply this by 2. Actually, we don't have to. Okay. We don't have to multiply this by 2 because we could just subtract 2 times this row from this. It would be upper triangle, right? So we have a choice, actually. Well, let's go with the easy choice. We don't have to do 2 steps. Okay. Let's add -2 times number 2 to number 3. So, okay. Because it's this matrix, right? Because again, we just do this to the identity matrix. I did it here in here explicitly, but we do the same thing. And I think you understand that. So E3 multiplied by R1, I have 1/2, 0, 1/2, 3/2, 0, 1, 4, gives us what? Well, double this row subtracted from this gives us a 0. Well, first of all, I'm not going to affect the first two rows. Let's write them down. 1/2, 3/2, and then 0, 0 is -2 times this is -1 added to 1, and -2 times this is -3 added to 4 is 1. Okay, that's upper triangular. Okay, well, then we can say, so that E3 multiplied by this matrix, which is E2 multiplied by this matrix, right? Which is E1 times our A matrix, and let this be A, equals the identity. Okay, now, specifically, step by step, we can then express A as a product of inverse elementary matrices times I. Okay, now the way that works is E3 inverse times E3 E2 E1 A equals E3 inverse times I. So this is really neat. You know, if this doesn't strike you as really neat, then you probably need to be an engineer. Okay. Okay, well, I'm insulting engineers, but I don't really mean that. Just like to kid them a little bit. Because usually engineers don't care about the aesthetics. Many of them do. And I think you're a better engineer if you do. This is aesthetically very beautiful and pleasing. Okay, so try to understand that. Well, this is just then I times E2 E1A equals E3 inverse times your identity, which is just E1 E2 or E2 E1A equals E3 inverse times your identity. Then we multiply by E2 inverse. Okay. And dot, we can write out these steps. This is I, just like it was up here, right? And that just leaves you an E1A here. So make sure you understand that, so you could write this out. And you know what? Writing things down without thinking, and I'm so concerned I keep doing that. So feel free to say, hey, whatever you think of. It doesn't equal the identity matrix, it equals this matrix, right? So 1, 5 halves, 1 half, 0, 1 half, 3 halves, 0, 0, 1. And that's the upper matrix. So I don't want to write upper. I don't want to write out the upper matrix every time. So I'm just going to use U to stand for this matrix. Okay. Well, then the last step, I didn't leave myself room to write. But if we come up here, we see that A is going to equal E1 inverse, E2 inverse, E3 inverse times U. Okay. Now, And you can verify this for yourselves. Every one of these elementary matrices is lower triangular. Okay. Where's E1? There it is. It's diagonal, so it's lower triangular. Lower triangular means there's nothing above the diagonal, right? Except zero. The zero is above the diagonal. This is lower triangular. And this is lower triangular. Well, I'm not going to prove it. You can prove it to yourself, and you should. When you multiply two lower triangular matrices, you get a lower triangular matrix. So that E1, let's say E2 inverse times E3 inverse is lower triangular. Then you should actually multiply out these matrices and see why. See what the pattern is, and then see if you prove it in general. And E1 inverse times that product is again lower triangular times lower triangular, which is lower triangular. Okay, so this is big L means lower triangular. So what do we have? We have lower triangular times upper triangular. Well, again, given my well-established inability to plan out board space, I don't have much room to write this, but I'll just say that this is kind of all this off its line. This is lower triangular times upper triangular. Big deal, you put those in this. Detail explaining why. Okay. But basically, the most efficient computer algorithms will first, if they're trying to do something with this A matrix, often solve an equation using the matrix or whatever, they'll reduce it to lower upper triangular first. I'm going to show you why they do that. Okay, make a decision here. Okay, so solve LUX equals V. First solve LZ equals V. What's Z? Something that I throw in there. It's a dummy variable, if you wish. It's just there to use in the process. I could call this thing anything, okay? Doesn't have a previous definition. It's just the variable you get when you solve this equation. Or well, it's a variable you use in order to solve this system. Let me try to be as clear as I can about this somewhat confusing process, okay? If I'm clear enough about it, maybe it won't be confusing to you. Okay, you solve this, okay? Solve this equation and solve UX equals Z. Now let me make sure I did that right, make sure that makes sense, because it's even confusing, because there are two ways you can look at this. Pretty sure that's right. Because when you solve LZ equals B, you find what UX has to be. Okay? And then that's Z, UX has to equal Z. Okay. And then you solve ux equals z, because ux has to be z. So, and the reason this is so efficient is it's really easy to solve by back or forward substitution. If you solve this by forward substitution, you can solve this by backward substitution, and you don't have to do any extra work. And a computer can do that much more quickly than any of the alternatives. Well, I won't say any of the alternatives because I can't prove that there isn't an alternative. Okay, but since they all use it, there must not be. Nobody's discovered an alternative, and I think it's probably been proven. But I don't think it'd be that hard to prove. But I haven't tried to prove it. Okay. So another way to look at it. Let ux equals z. Totally equivalent. It might not seem like there's much difference, but it's a little different in the way you see it and think about it. You can think about it either way. If you let ux equals z, then Lux equals z becomes Lz equals z. Okay? Easy to solve. With forward substitution. Okay? Then, of course, ux equals z. Why does ux equal z? Because you said it was. Okay? Because that's the substitution that you use to solve this equation. Okay? So that's the process. And I'm going to ask you to do the system this way. Okay? Matter of fact, I'll give you the system right now. Write this down, and I'm going to ask you to do this and bring it to class with Tuesday. Okay? So, this is your own system using your A, B, and C numbers. That'd be nice. We'll put a 1 here. Much like the example I did. Okay? Your elementary matrices will be a little different. Put those examples. Okay? And I'll also say that I don't know why. I don't know what causes this video to be used a lot, relatively a lot. The video I did on LU decomposition gets viewed somewhere by somebody about 1,000 times a year. Maybe it's just one person that really loves that video, watches it 3 times a day, but I don't think that's it. Also, there's a small error in that video. Okay. So maybe they're just watching it so everybody can laugh at it. That's all right. I deserve it if I made a small error in that video. But I don't see anything special about the video. I'll probably ask you to watch it. See if you see anything special about it, except it's a pretty clear explanation of the process. Except I don't really emphasize the fact that you can't switch rows. And it comes down to, if you switch rows, you mess up the process, because the process, if you switch rows, you mess up the upper and lower aspects, because upper and lower forms. Okay, and you can, it's pretty obvious why. If you just switch rows, you see. Okay. You won't get a matrix equivalent to the original matrix that's in LU. That's what it comes down to. And if you play around with it, you can see why that is. You have time to play around with it, it's worth doing. Let's see that again. Just make sure we got it. So value x equals b, and it doesn't hurt you here the third time. You first solve LZ equals b, because that tells you what you got to multiply L by in order to get to it. Okay. Of course, you're multiplying L on the left. You're multiplying on the left ux by L, so ux would have to be z. Another way to say it, substitution. Let ux equals z, so that LUX equals b becomes LZ equals b, which can easily be solved by substitution to find z. And then, of course, ux equals z because you said so. It might be the third time it's on the video. And we're going to solve this matrix then by LU decomposition. Okay, very good. Okay, same dynamic. Same dynamic. 1,000 immortal people on an island, okay? Or at least 1,000 people that live long enough that the model will work, okay? So no reproduction and nobody dies. I'm not sure that's a good trade-off. Okay, so 1,000 immortal people on an island. And every month, %10 of the same people become demented. Another thing I should have said first is that everybody's either sane or demented. Makes it an interesting island. Okay. And 20% of the demented become sane. Okay. Now you would think that if more demented are becoming sane, then eventually everybody would be demented, right? Or everybody would be sane. Okay. You might think that, but really, you approach a state where you have twice as many sane as demented, because then 20% of your demented would equal 10% of your sane. So you just be switching equal numbers. Okay. Well, I'm going to abbreviate the method for the sake of time and space. If S is a number of sane and D is a number of demented, And S prime is the number sane after a month, at the end of the month or whatever, a month later. D prime. And then I can say that the vector and then I'm going to write it up in the opposite order as I usually do. 0.9.2 times SD equals S prime. Okay? Because 0.9S is 90% of your sane people who stay sane. So they go into the sane category. And 20% of your demented people become sane. So the 0.2D becomes sane. So actually, maybe we'll write this out as 0.9. Looks like a 0.95 and F still looks like a 5. That's okay. Okay. And you could write the matrix products for the number of demented. I guess I've got room to squeeze it in. This is 0.1S plus 0.8D, which equals D prime, okay? Total number of people you have doesn't change. Because here's 0.9 of your sane and here's the rest of your sane, right? They're in different categories, some of them in different categories now, but you still have your total number of sane if you add these up, right? And if you add these up, you still have your total number of demented. They don't change. Well, the whole model doesn't have to be written as two equations. We can write this as the matrix. Okay. Now, after 2 months, well, we're going to multiply this matrix by the new number of sane and demented. Okay, it's another month. We got different numbers. Of course, this equals this matrix times your original number of sane and demented, right? So you multiply, this is the S prime D prime, right? Multiply that by the 0.9, 0.2, 1.8, and you get the number after 2 months, okay? Well, you can see that let me, I want to extend this, but we're going to write one more. And this equals the square of this matrix times the SD. Okay, well, At the end ones, we have, what do you think, 0.9, 0.2, 0.1, 0.8 to the n times SB. Okay. Well, as it turns out, and we can't go into it now because we've got to do the eigenvalues and eigenvectors and geometric interpretations and all kinds of stuff that gives you deep insight. Okay. I can do that. I usually do this whole thing at the beginning of the course. Well, I'm locked into WebAssign, and there's so many assignments we don't have Slack to do that. I've locked myself into it. I don't have to be locked into it. Okay. But I'm doing that. I'm not totally happy with it. Parts of it I am happy with. Okay. Again, I think the problem assignments are too straightforward and they're just not deep enough. But anyhow, you have this. Okay. Well, you'll see the notation, but if you understand this, you'll understand what you read in section 2.5. Okay. And the problems are pretty easy. Now, they also go into 3 categories. Okay. You go into as many categories as you want. Let's say you have sane, demented, and borderline. Okay. Now, borderline personality disorder is got a complex definition and doesn't really fit. I don't think. I don't know that much psychology. We'll say borderline between sane and demented, not clinical borderline personality disorder. Okay. Then you would have a 3x3 matrix. Okay. Now, one characteristic of these matrices is we see these things, you know, this and this add up to just S plus D, right? This number and this number. If I add these expressions, I just get S from this and I get D from this. Okay. Well, you call this a stochastic matrix. And you call the resulting matrix stochastic because the matrix has that characteristic. There's your 0.9 and 0.1. They add up to 1. The 0.2 and the 0.8 add up to 1. Common sense why they should add up to 1. If you've got 3 categories, then you have a 3x3 matrix for sane, demented, and borderline. Everything I said still works. It's just the matrix configured. Okay. And the shortcuts are used to find the nth power of the matrix. Still work. Okay. You know, to simply diagonalize the matrix, easy to take a nth power of the diagonal matrix. You just take the nth power of all the things on the diagonal, everything else is 0. And then you transform it back. And we'll see that somewhat later in the course, probably around late March. Okay. So that's the idea. It's an important idea. And well, I've left myself almost no time to talk about determinants. That's going to be due on Tuesday. We've got to talk about it. Okay. There are several problems on determinants, but basically you just got to know a couple things. So I think I can illustrate for you in the 11 minutes we have left. First of all, this diagonal minus this diagonal. We've seen that. That came out of my derivation, my partial derivation. Hopefully accurate up to the point where I stop. Okay. That had this in the denominator of, you know, second row of that inverse matrix. Okay. Each element had this in the denominator. So it's an important quantity. Okay. That's your determinant. Now I'm just going to illustrate this rather than writing the definition, so that when you see the definition, you understand in terms of what I'm illustrating. Okay. Now let's going to do one with numbers. 1, 2, 3, 4, 1, 6, -5, 2, 2. Okay. To get this determinant, this 1 times the determinant of 1, 6, 2, 2. Now, I'll tell you why the pattern is, won't actually derive it for you. And I want to rewrite that. We have a little more to on this. -1 is a 1 plus 1. And I'm going to change this 1 to a 7. -1 times 7 times the determinant of 1, 6, 2, 2 matrix. Okay. Now, why a 1 plus 1 up here? Because 7 is in the first row and first column. Okay. So that's a 1 plus 1. Why the determinant of this matrix? Because if I throw out the row of the 7 and the column of the 7, that's what I've got left. Okay. So it's a very simple process. It will become clear when I do the next term. I do -1 to the 1 plus 2 because I'm going to use 2. I'm going to use the second number in the first row. So what I'm doing is I'm expanding this determinant on the first row. Okay, so the next number in the row is 2. It's the 1, 2 element, right? So it's -1 to the 1 plus 2. Times 2 times the determinant of the matrix I get if I throw out the column below 2 and the row of the 2. And that leaves me with the 4 and the -5 and the 6 and the 2. And then it's going to be plus -1. So I'm going to go to the third number in the row. And that's going to be 1 plus 3. That's going to be -1 times 3 times the determinant of what I get when I throw out the row and column of the 3. Well, I'm throwing out the first row. And then in addition, I throw out this column, leaves me that 4, 1, -5, 2. Okay. Now that's easy to calculate. You know how to do a 2 by 2 matrix. You just use this. You know, doing all the theory that connects it, but take my word for it, it works. I don't think your book really proves it even. If you really want the proof and we have time, ask and we'll do it. Okay. Well, this then equals 1 times 7, and this determinant is 2 minus 12. If I did my arithmetic right. Okay. Now -1 to the 1 plus 2, well, that's -1 cubed. So you're going to have 3 negatives, so it's going to be -1, right? It's going to be -1 times 2 times this determinant. Now, hopefully I do this accurately, but that's 8, and that's negative, so that's 30. So that's going to give us 38. That's going to be 1 to the 4th power, which is -1 to the 4th power, which is 1, times 3. And this determinant is 8, and 5 is 13. Okay. That's how you calculate it. Now there's some words. Okay. Call these three matrices minors. This is your 1, 1 minor, your 1, 2 minor, and your 1, 3 minor, because it came when you omitted the row and column of the 1, 1, 1, 2, and 1, 3 elements. Okay. The cofactors right this way. This I'm going to call this the M1 1 minor, M1 2 minor, M1 3 minor. Okay. What are your cofactors? There. Okay. And we call these C1 1, C1 2, and C1 3. Okay. Just a terminology that's handy in referring to the matrices. The process is the same, no matter how big your matrix, as long as it's a square matrix. You can't do it if it's not a square matrix, because if you try to do it without a square matrix, you never get down to a 2 by 2 matrix. You can think about why and test that yourself, but it's pretty obvious if you want to think about it. Okay, so if I've got a 10 by 10 matrix, well, my first minor is 9 by 9, right? All my minors are 9 by 9s. So all my cofactors are 9 by 9s. And the determinant is just, you multiply these numbers by the cofactors, basically. Your book will tell you that. Okay, make sure you read it. Try to make it easy for you to read the book and get what you need to do the relatively easy problems. That's simple problems. I'm not unhappy with WebAssign's problems on section 3.1. Okay, aren't bad. So if you have a 10 by 10, you're going to reduce this to a bunch of cofactors involving 9 by 9. Okay.
Are you in class right now?
Huh?
This is class right now?
You'll have linear algebra class.
Oh, no.
You want some, keep coming.
No, it's all right. I'm just gonna run over. I'll be
Yeah,
back.
yeah.
I'll be back.
Just walk from and have a seat. Just don't walk in front of the camera. Hold on. He's not in this class. He's in the next one. So if he walks in front of the camera, no big deal. Okay. I'm not going to tell him that. Okay. Okay, so anyhow, you see that your cofactors for 10 by 10 would be 9 by 9s. And you'd have 10 of them, right? And then each 9 by 9 has 9 cofactors. So now you got 10 9 by 9 cofactors, each with 9 8 by 8 cofactors. You got 90 matrices, okay? And they're all 8 by 8. And then you're going to have 8 7 by 7s and 7 6 by 6s. So you're going to end up with like over 1 million matrices, which is why you try to look for shortcuts for calculating determinants. And a lot of them are related to elementary matrices. We'll see a little, next week probably. And they're all just kind of neat. And these things have interpretations. If this is a three-dimensional space and defines a transformation of three-dimensional space, okay? Take our three-dimensional space and transform it. Well, what's this number? That's negative 70 and minus 76 and plus 39. That's negative 100 or something, right? That means space would get 100 and some times as big. Everything would be inflated, 100 and some. Okay, you don't have to understand why at this point, but probably talk about that. Also, everything would be inverted. Right hand would become left hand and all kinds of things would be inverted. Okay, so it can't be a backward three-dimensional space. Okay, you don't usually as engineers transform things into backward inflated spaces, but that picture can be real handy for understanding some things you do in physics and engineering. Okay. And, we won't be able to go too deep into those applications, but if anybody wants to look at it a little further, I love it, so I'm happy to do it. Okay. Okay, well,